But then, you know, since you're at home, most of you guys stay at home. I mean, I think this make no difference. I think whether you holiday or not. Okay, your life goes like normal. Okay, today again I will again to explain to you the applications of spring and also electrical after this. Whatever it is, okay, you just try to grasp the concept, okay, the concept how to apply differential equation in real life problems. We don't limit ourselves to these two problems. Actually, there are other problems that have the same characteristic as these two problems that you can apply to them as well. Okay, but kita belajar ni just nak get the feelings how to apply this in your real life problems. Okay. um, in the last meeting, we're talking about the spring, right? We're talking about restoring force, which is equal to minus kx. Okay, we use what? We use Hooke's law. Okay, k is the spring constant, and x is the amount of displacement. Okay, the distance of displacement. And then from the Newton's second law, we know that F equal to ma. Okay, you learned this from physics, your form 4 physics. Okay, F equal to m times a, where m is the mass and a is accelerations. Okay, so a equal to d square x dt square. Okay, this is a. Okay, so this is equal to the force. So you replace restoring force with m d square x dt square. So equal to minus kx. Okay, in the first situation, we don't consider any other external forces. Okay, this is harmonic motions, right? So you have md square x dt square equal to minus kx. You bring kx to the left hand side, become md square x dt square plus kx equal to 0. Before I forget, please make some dua to your friends Abdul Rahman. He's now hospitalized. Okay, make dua for him for quick recovery. Okay, so m d square x dt square plus kx equal to 0. This is homogeneous second order linear with constant coefficients. To solve this, we change this into characteristic equations or ordinary equations. So mr square plus k equal to 0. So your r equal to plus minus square root of k over m times I. So I square root of k over m. Okay, or you can write as plus minus omega I, where omega is equal to square root of k over m. Okay, so we have complex roots, all right, where alpha is equal to 0. Okay, beta is equal to omega, which is equal to square root of k over m. Okay, so xt, so in this case, xt, displacement. Before this y, now xt. Before this yx, now xt. Okay, xt equal to e power of alpha t. Okay, e power of alpha t, because now dependent variable is t, but alpha is 0. So alpha e0 is equal to 1. So we have 1 times c1 cos, okay, cos beta t plus c2 sines beta t. Beta now becomes omega here, or becomes square root of k over m. Okay, so also we can express this as xt a cos omega t plus delta. Why we want to change this? Because when you change this, we have where a represent the amplitude. So how much lower and high it can goes, and then omega denotes the frequency. So how frequently that it move in this interval, and then of course delta is the angle. So this is harmonic motions. Okay, we did example 1 before, right? Example 1, when we move, when we stretch, okay, the spring from 0.5 to 0.7. That means x of t, okay, x of 0, okay, x of t when t 0 is equal to 0.2, okay, and then and then what else? Okay, so in this case we need to find the Springs constant, because k times x equal to 25.6. Okay, this is Newton. So k we have like 128. So we replace, okay, we go to these equations. Okay, we replace m with 2, k with 128. So we have, okay, 2 dx d square x dt square plus 128x equal to 0. Okay, in this case, okay, we have 2, okay, we have 2r square, okay, 2r square plus 128 equal to 0. That means 2r square equal to minus 128. So r square equal to minus 64. That means r equal to, okay, plus minus 8i. Okay, so that means alpha is equal to 0 again. So that's why you have xt equal to c1 cos 8t plus c2 sine 8t, because your beta is equal to 8, right? All right, and then to find that this one is what this is the general solutions. Okay, to find the particular solutions, okay, you have to derive by your own from this. Okay, from this statement, we know that when t equal to 0, okay, x equal to 0.2, because 0.7 minus 0.5 is 0.2. Okay, and then with initial velocity is equal to 0, that means when t equal to 0, dx dt again equal to 0. So we need two conditions to solve second order ODE to solve for C1 and C2, right? So when x not equal to 0, okay, from here we know that, okay, from here we know that, okay, we have x naught equal to C1. So C1 equal to 0.2. Okay, you replace here, okay, 0.2, and then you have cos 0 is equal to 1. 1 times C1 is C1. This one we have 0. So that's why you have C1 equal to 0.2. Okay, and then to use the second condition, of course, you need to take the first derivative of this, which is equal to minus 8c1 sine 8t, okay, plus 8 cos c2 cos 8t. So we have this one, and then we replace, okay, when t equal to 0, x prime 0 is equal to 0. From here, we replace t with 0, we have 0 there. So 8c2, okay, cos 0 is equal to 1. So 8c2 is equal to 0. That means c2 equal to 0. So this is our final particular solutions. It describes the displacement, okay, with respect to time. Okay, in the first case, we have harmonic motions. Okay, in the second case, we have damped vibrations. That means we have external force. Okay, in this case, when we have vertical motions, okay, we have damping force. When we have horizontal motion, we have frictional force, right? So now we focus on vertical motions. So we have the damping force. So the damping force is equal to minus c times dx dt, where c is the positive constant. We call it damping constant, right? So in this case, we have two kinds of forces, which is restoring forces. We got in the previous example, plus damping force, right? So force, which is equal to md square x dt square, okay, force equal to now minus kx minus c dx dt. So we have these extra terms, minus c dx dt. Bring all terms to the left hand side, so we have md square x dt square plus c dx dt plus kx equal to 0. Again, we have second order linear with constant coefficients. because M is constant, C is constant, K is constant. Okay, now homogeneous, right? So again, we can use the technique you learned in chapter 3, earlier in the chapter 3. So we can transform this into characteristic equation or other equation. So mr square plus cx plus cr plus k to 0. Then you have two roots. Okay, you have two roots. All right. So it depends on the terms inside this square root, okay, which is c square minus 4mk, right? So we refer to the previous method in the early chapter 3. Okay, when c square minus 4mk greater than 0. Okay, or before this we have b square minus 4ac greater than 0. We have two distinct real root. Okay, but for springs problems, we call it over damping. Okay, when c square minus 4mk greater than 0, we have over damping. Okay, so we have a distinct real root. Why real root? Because this terms is greater than 0. Okay, the terms inside of square root greater than 0. We have two distinct real root. I also explained to you that, okay, since all c, m, and k are positive, this implies that c square minus 4mc, okay, is less than c square root. Why? Because, okay, c square minus 4mk, okay, 4mk is positive. So c square minus positive must be less than c square. So all these terms must be less than square root of c square less than c. Okay, and then it's also both the roots are negative. So R1 and R2 are negative. Why is negative? Okay, because these terms, okay, these term here less than c. Okay, this term here square root of c square minus 4mk less than c, and you plus minus c. So this minus c will dominate these terms. So we have minus. Okay, you have negative on the top. Okay, denominator is positive. So negative over negative is positive. The same apply here. Negative minus negative is negative. Okay, over positive is negative. So both roots are negative. Okay, and that's why, okay, when x goes to 0, okay, as t goes to infinity, x goes to 0. That means the amount of displacement tends to stop, 0, no move, right? There's no movement. Okay, so why this goes to 0? I explained last time, because ER1T, ER2T, this R1T, R2T is negative. So if negative, we can transfer to the denominator. Okay, so it becomes C1 ER1T. Okay, the denominator becomes large as t goes to 0, and C1 is constant. Constant divided by very large number approaching 0. Okay, the same thing here. Okay, constant over very large number approaching 0, both approaching 0, and that's why x approaching 0, st approaching infinity. All right. So for overdamping, okay, shown in figure 4, the first figure of figure 4, overdamping here, normally in this case, like tidak ada lanjutan, spring itu dia tak oscillate, right? Dia terus pergi kepada the stop. Okay, dia tak injek, dia pergi macam tu, alright? So this because c square minus 4ac, okay, c square greater than 4mk. C square is what? The damping force, the constant damping force greater than 4 times of the mass and also spring constant. Okay, So that means spring constant is stronger, okay, than the spring mass and also the spring constant. So it dominate. So bila dia tu dominate, damping force dominate, that mean they slow down the motion. That means dia tidaklah terus dia tak oscillate langsung, right? And that's why you got this graph here. Okay, the second case when c square minus 4mk greater than 0, okay, that meaning that now c square minus 4mk equal to 0, then we have r equal to minus c over 2m. So we have repeated root. We have repeated root, which is minus c over 2m. Okay, sorry, here minus c over 2m, right? So this is so x equal to what? X equal to minus c over 2m times t, okay, and then c1 plus c2t, okay, because no, your now, right? So this one is the same, okay. So we can take that out. So that's why we have this. So this is the solutions, okay. For this, okay, it's the same, similar to the over damping. Okay, case number 2 is called critical damping. It only isolate once, and then it goes to the it stop. Goes one and it stop. It only isolate only once. Okay, and it stop. Okay, this is critical damping. Okay, when c square minus 4ac less than 0, so we have under damping. Okay, for this under damping, you have some acceleration. Okay, you isolate few times before it stop, right? So for under damping, of course we have complex root. Okay, complex roots, we have minus c over 2m plus minus square root of k over 2m I. So omega I. Okay, we have this. Sorry, omega is Omega is all right. Actually, so we have c square minus 4mk over 2m because we put I there. So we reverse the order. So become 4mk minus c square. So the solution is this. Okay, x equal to e minus c over 2mt, okay, c1 cos omega t plus c2 sines omega t. Okay, so now we have, okay, there are some oscillations. Okay, this is e power of minus c over 2mt is the what? Is the amplitude, right? Amplitude, it will goes up and down. Okay, now since c greater than 0, again, c greater than 0, okay, and then m also greater than 0, okay, that means minus c over 2m is also greater than 0, okay, because c is positive, m is positive, so c over 2m is positive, so minus positive will be minus positive will be negative, so the whole thing is less than 0, meaning that e power of minus c over 2m times t also goes to 0, okay, as t goes to infinity. Okay, so this one will be 1 over c power of 1 over e power of c over 2mt. Okay, the numerator is getting larger and larger. Okay, it will goes to 0. Okay, so that's why x goes to 0 when t equal to infinity. So you have to really understand this kind of movement. So that mean that this term goes approaching 0. So that means it will stop. Okay, as this goes to 0, it will stop. But of course, and then this one is what? This is frequency, right? So it will move. Okay, it will move up and down, and down, and finally it will stop. Okay, so this when you have under damping force, under damping movement. Okay, so let's try example 2. Okay, Suppose that the spring of example 1 is immersed in a fluid with a damping constant C. So it immersed, okay? So it immersed in the, let me see here. Where I want to find where is the diagram? Let me see the diagram. Okay, it will immerse in the underwater. Okay, and then C equal to 40. Okay, find the position of the mass at any time t if it starts from equilibrium positions and is given a push to start it with an initial velocity 0.6 millimeter per second. Now your dx dt is your velocity is equal to 0.6. Okay, when t equal to 0 now. Okay, m remain unchanged, so m equal to 2. Okay, spring constant is 128. So when you go up here, so you replace m with 2, okay, and then c with 40, and k is equal to 128, right? So you get this equation here, okay, and then of course, you can reduce this. Okay, you divide all terms with 2. You reduce to d square x dt square plus 20 dx dt plus 60 for x equal to 0, right? So, so you transform this into characteristic equation. So you have r square plus 20r plus 64. Okay, and then here you can use quadratic formula, or you can factoring. Okay, so you have r plus 4 times r plus 16 equal to 0. So you have both roots are negative, minus 4 and minus 16. Okay, and then xt will be c1 er1x, so e minus 4, sorry, e minus er1t, so e minus 4t plus c2 rt2 r2t, so c2 e minus 16t. So this is the displacement. Okay, this is general function. Okay, to find this particular solutions, a particular movement or displacement. Okay, you know that when x equal to 0, x equal to 0, when t equal to 0, okay, x equal to 0. Okay, in this case, equal to must, right? Equal to 0. So see from here, we replace x equal to 0 here, t equal to 0 here. So we have 0, okay, equal to c1, e, so e0 is equal to 1. So c1 plus c2, because e0 is equal to 0. So you have 0 equal to c1 plus c2. Okay. And then to use the second initial conditions, which is v equal to 0.6 when t equal to 0, we have to differentiate this once. We differentiate this once. Susie, I'm having class, Susie. I'll call you later. I'll call you later. All right, so now we have x prime t equal to minus 4c1e minus 4t, and then minus 16c2e minus 16t, right? And then we replace here, okay, when t0, x prime, that means v. Okay, v equal to minus 4c1, this one is 0, minus 16c2. Okay, e minus 0 is 0. So we have minus 4c1 minus 16c2 equal to 0.6. So we have two unknown, okay, two equations. Okay, the first one is c plus c1 plus c2 equal to 0. The second one is is minus 4c1, okay, minus 16c2 equal to 0. You can either use eliminations or you can use substitutions. Okay, in this case, the book used substitutions. Okay, from here, from C1 plus C2 equal to 0, we have C2 equal to minus C1. So you replace C2 with minus C1 here. Okay, now you have, okay, now you have minus minus become plus. So we have minus C1 plus 16 C1 equal to 0.6. So we have 12, 6, 12. So minus minus become plus. So minus 4 C1 plus 16 C1. So we have 12 C1. Okay, 12 C1 equal to 0.6. So that means C1 equal to 0.6 divided by 12 is equal to 0.05. So C1 equal to 0.05. Okay, and then C2 will be minus 0.05. Okay, so you just replace there, you take 0.05 out. So this is your final solutions. 0.05 times e power of minus 4t, okay, minus e power of minus 16t. Okay, actually here you have C1, which is 0.05, e power of minus 4t minus 0.05 e power of minus 16t. You take out 0.05, and that's why you have minus over there. Okay, so this is for underdamping. Okay, how about, besides we have two kinds of forces, which is restoring forces and damping forces. There are another external forces, we name it F of t. Okay, another forces, right? We call it F of t. Now, M of A, now we expand this, okay? And M of A, which is F, now become equal to, you have restoring forces, you have damping forces, and then you have external forces, okay, denoted by F of t, right? And then you bring minus kx minus c dx dt to the left hand side. So now we have md square x over dt square plus c dx dt plus k dx equal to f of t. Now we have second order linear constant coefficient, but we have what? Non-homogeneous. Okay, now we have non-homogeneous. How to solve this? Again, you can use what? Undetermined coefficients. You can use a version of parameters, or you can use reductions. Okay, so you can use the method that you learned for non-homogeneous to solve these kind of problems. Right. All right. Let's move on to electric circuit. Okay, electric circuit. They are this problem is similar to spring problems, but the terms that they use is different. Okay, if you convert to mathematics, it's almost the same, but of course the parameters are different. Okay, so let's refer to figure 7. In figure 7, we have E. Okay, what is E? E is electromotive force. Okay, E. Okay, supplied by a battery or generator. So E. Okay, so it's electromotive force. And then we have R. R stands for resistor. Okay, and then we have L. L is inductor. Okay, and then you have capacitor C. Okay, so this is like series of circuit. Okay, and then okay, if the charge on capacitor at times t here is times t is Q equal to QT. Okay, the capacitor is Q equal to QT. Okay, then if the charge on capacitor Q equal to QT, then the current, okay, the current is defined as the rate of change of Q. Okay, the rate of change of capacitor with respect to T. Okay, so we involve rate of change. So anything involving rate of change, we can express in terms of differential equation. In this case, we call it dq dt. Why? Because it only depends on t. So we have ordinary differential equations. So current is equal to dq dt. Okay, and also you learn from physics in Form 4, okay, the voltage drops, okay, across the resistor, okay, inductor and capacitor is defined as R times I, okay, and then L, okay, L di dt and Q over C. Okay, this one respect to resistor, this term respect to inductor, this term respect to capacitor. The voltage drops. Okay, and then according to Kirchhoff voltage law, he said what that he said? He said that the sum of this voltage is equal to the supplied voltage. The sum of the voltage equal to the supply. The sum of this voltage drop. Okay, that means the loss of voltage equal to the supply of voltage. Okay, so now we have these equations. Okay, so we have all this. Okay, L di dt, okay, plus Ri plus Q over C, because this the voltage drop must equal to the sum of equal to supply of the voltage. Okay, equal to E of T, because E of T is equal to supply of voltage, right? All right, so ET equal to this. Again, what? This is what? This is first order ODE, okay, with constant coefficient. To solve this, you can use the technique you learn in chapter 2. Okay, chapter 2. Dependent variable is what? T, right? And then, sorry, independent variable is T. Dependent variable is what? The current, which is I. Okay, so I is the dependent variable, T is the independent variable. All right, you learn this. Okay, now, but since we are dealing with second order, okay, we try to, okay, now we know that from here, I is equal to dq dt. Okay, I is equal to dq dt. We will express this in terms of, okay, in terms of dq dt. Okay, because we replace I with dq dt. Here I is equal to dq dt, and that's why now it's become L d square q dt square plus Ri become R dq dt plus Q over C, we write as 1 over CQ. Okay, because we just replace this I with dq dt, and then that's why we have this. All right, so this what? This is what? Second order. Okay, second order linear with constant coefficients. Okay, when the current is 0, it's become homogeneous. Okay, when it's not 0, become non-homogeneous. Okay, to find the initial conditions, of course, okay, if the charge Q0 and the current Q0 are known at times 0, then we have when T0, we have Q equal to Q0. Okay, when T equal to 0, I0 equal to I0 equal to I0, but I0 equal to dq dt. So q prime 0, which is dq dt, equal to I0 equal to I0. So this is initial conditions. Okay, when the current and also the charge is known at times t equal to 0. All right, now, okay, now you said here okay, this one is with respect to q depend on t. Okay, we also know that I is equal to, okay, if we differentiate equation 7, okay, if we differentiate equation 7, okay, we now will have, okay, L d cube d cube q dt cube. Okay, we differentiate again equation 7 with respect to t. Now we have L d cube q dt cube plus r d square q dt square, okay, plus 1 over c d, okay, d prime. Okay, this one q prime, or dq dt equal to e de dt or e primes. So, but this cube q dt cube is the same as d square I dt square. Because when you replace I with dq dt, you will get d cube q dt cube. Okay? And then when you replace d square q dt square, you will get di dt, because I equal to dq dt. So this is the same as d square q dt square. And then, of course, dq dt is equal to I. Define this, okay? Because I equal to dq dt. Okay, this, how to derive it, this really explains your understanding of differential equations. All right, and then now dx dt is equal to e prime t. Okay, so we have equation 1, we have this, we have equation 7, and then we have also these equations. Okay, but the most important one is equation number 7. Okay, let's try this. Okay, find the charge. The charge, that means find Q. Okay, because Q is the charge, and current at times t, that means t is the independent variable. We want to find the charge and current. We want to find qt and it at times t in the circuit of figure 7. Okay, this figure. Okay, if R resistance is what? 40 ohm. Okay, and then L is equal to 1, and then C equal to 16 times to the power of minus 4. Okay, this is the unit for these two. And then F E of t is given that the current, okay, is equal to 100 cos 10 t. Okay, 100 cos times c. So we refer to this equation 7. We replace ET with 100 cos 10t. Replace this ET with 100 cos 10t. Okay, now R equal to 40. Replace this R with 40. We replace this C with 1 over 16 times 10 to the minus of minus 4. So we will get what? We will get 6 to 5. Okay, 6 to 5 Q. Okay, so 1 over 16 times 10 to the power of minus 4, we will get 6 to 5. And then L we replace with 1. Okay, so now we get this. Okay, this comes from equation number 7. When you replace L with 1, okay, we replace R with 40, and then 1 over C we replace by 6 to 5. Okay, equal to 100 times cos 10t. All right. Okay, now you know that this is second order. Okay, linear constant coefficients. Okay, with non-homogeneous. Okay, with non-homogeneous. Okay, first you need to find what? YC. Okay, so you make this equation equal to 0. Okay, to solve for homogeneous. So now we change this into auxiliary equation or characteristic equation, become R square plus 40R plus 6 to 5 equal to 0. And then here you find the root here. Okay, minus b plus minus b square minus 4ac divided by 2a. So we have minus, okay, 900, okay, over b square. That means 40 square. That means 1600 minus 4 times 6 to 5. So you have minus 900 over 2. You can simplify this. Okay, you will get minus 20 plus minus 15i. So this one it will be what? Will be 30 divided by 2. That's why you got 15 there because it's negative I there. And then minus 40 divided by 2, you have minus 20. So minus 20 plus minus 15i. So that means alpha is equal to minus 20, beta is equal to 15, and that's why QCT. Because we're talking about Q, right? Q, the charge. Okay, QCT now becomes minus 20, E minus 20t, C1 cos 15t plus C2 sin 15t. Because this is your beta. Beta is 15, alpha is equal to minus 20. Okay, and then we need to find what? To find what QP. Okay, QP. Okay, you refer to the table. You refer to the table. Here is what? Combination of polynomial of order 0 and also trigo. And then that's why the form like this. Okay, constant times cos 10t and then plus beta times sine 10t. Refer to the table. So this is your QP, your trial solutions. And then you need to compare QP with QC. They are not the same. But this one is which is cos 15t, this one cos 10t. They are not the same. So we stop. Okay. So this is your QP. Okay. And then of course, okay, we need to differentiate QP once and twice. Okay, and then we plug into here. Okay, to get the coefficients, to get the value of A and B. Okay, QP equal to A cos 10t plus B sin 10t. QP primes is equal to minus 10A sin 10t. Okay, you differentiate because you have minus sin t, sin 10t, right? And then plus, okay, b cos 10t times 10. So 10b cos 10t. Okay, for you differentiate one more time, you will get QP double primes is equal to minus 10a cos 10t times 10, 10 times 10, which one equal to minus 100, a cos 10t, and then 10 b minus sin 10t times 10, so minus 100b sin 10t. Okay, so you replace this, okay, d square q dt square with this, all this term, and then dq dt with this, and q with this qp. Okay, replace in equation 8. Okay, the same as we did before, except now it's we're dealing with electric circuit. All right. So now we replace here. We will get this, right, and simplify. We get this, and when we simplify, all right, we have for cos 10t, okay, cos 10t, so we have minus 100, and then we we have this 5 to 5a, okay, okay, plus, okay, 400b cos t, plus minus 400a plus 5 to 5b, okay, sin 10t equal to minus cos 100. From here, you get this, and then you compare the right and the left. Okay, now we compare the term involving cos 10t. That means 5 to 5a plus 400b equal to 100. Okay, so you can reduce this. Okay, you divide by 25, you will get 21a plus 16b equal to 4. Okay, and then the next one we have minus 400a plus 5 to 5b equal to 0. But there is no terms involving sin 10t on the right hand side. So this term will be 0. And then again, you reduce this, you divide by 25, you have minus 16a plus 25b equal to 0. So you have two equations, you have two unknown. You can solve for a and b. Okay, you can solve for A and B. and you will get A equal to 84 over 697. Okay, B equal to 64 over 697. Okay, and then you replace, you go back and replace A with this, with A with 84 over 867, and B with 64 over 697 here. Okay, and here, and then, okay, so you will get here, okay, because this one will be B's and D's, and then Q1 back, then we get that one. Okay, so QT, okay, because, okay, we have QP there, so this is your QP, but QT equal to QC plus QPT, like before, Y equal to YC plus YP. Now we're dealing with QT. So QT equal to QC plus QP. This is your QC, and then this is your QP. So we have the specific solution for, okay, for the charge. Okay, now this one is general solutions. To find this C1, C2, okay, we know that when T is 0, Q0 is equal to 0. Okay, when T is 0, Q equal to 0. So now we go here, we replace T with 0. So we have C1 plus, okay, 84 over 6897 equal to 0. So we have C1 equal to minus 84 over 697. Okay, to find C2, we use, okay, we differentiate this, we get current, okay, dq dt equal to current is I, okay, so we differentiate this, we will get these terms, okay, you just take the common differentiations, okay, and we, okay, and we replace t with 0, so we have I0 equal to 0 here, so we have minus 20 C1 plus 15 C2 there, because cos 0 is equal to 1, this one is equal to 0, okay, and then this one equal to 1, this one equal to 0, and that's why we have here, okay, 40 times 16 is 640 over 9697, okay, equal to 0. Okay, and then we solve for C2. C2 equal to minus 464 over 2091. Okay, so we replace this C1 with minus 84 over 697. This C2 with minus 464 over 2091. Okay, so the formula for charge is this, right? You just replace that one, right? And then for the current, okay, for the current, which is this is the current, okay, we just replace this C1 with this, with minus 84 over 697, and C2 with, okay, with minus 464 over 2091. Finally, we will get this. So this is for the charge, this is for the current. Okay, so this, when you understand all this, you will understand the whole thing. Okay, and as told you before, they are the same as the mathematical formulation before, except now it means different things. Okay, the variable mean different things, right? Okay, so this is the movement. Okay, because it now is depend on the what, on the QC and also on the QP. All right, we can understand this. Okay, but my main objective is this. If you compare equation number 5, equation number 5 involving springs problems. Okay, whereas equation number 7 involving current problems. Okay, electric problems, circuits, right? All right. In equation number 5, we have md square x dt square. M is the mass. Okay, this is displacement. Okay, and then C is what? C is the damping force. Okay, dx dt. Okay, plus K. K is a spring constant time displacement equal to F of T. F of T here is what? The internal force. Okay, internal force. Okay, the same thing here in equation 7. Okay, equation 7. Equation 7, L is inductor, or inductance. Okay, d square T, d square Q dt square. Okay, plus R is resistance, dq dt, plus 1 over C, 1 over C, okay, and then 1 over C, we call it elastance, okay, times the Q. Q is the charge, okay, equal to what? Equal to force. Okay, this one is electromotive force. Okay, you can see this in table. Okay, they represent the same second order, okay, linear, non-homogeneous. In spring system, we call it X, okay, with displacement. In electric circuit, we call it Q, this is charge. Okay, in spring system, dx dt is velocity, whereas in electrical circuit, dq dt is equal to current. Okay, the velocity in spring system equivalent to current in electric circuit. M equal to mass, okay, in spring problem. In electric circuit equivalent to L, which is in inductance in electric circuit. C is damping force in spring system equivalent to R, which is resistance in electric circuit. K is spring constant, but in electric circuit, 1 over C, which is elastance, okay? And for external force, Ft for springs constant, for electric circuit is Et, which is electromotive force, okay? So meaning to say that semua ini adalah second order, all this is second order linear constant coefficient non-homogeneous. So different problems, okay, they have different parameters. They mean of course the meaning are different, okay, but as far as you are concerned, they are representing second order linear constant coefficient non-homogeneous. Okay, so I have illustrated to you guys only two problems. Okay, spring and problems, and also electric circuit. Okay, and then we may also apply this, okay, in economy. Okay, like marginal cost. Okay, you can apply that also, I think, in your actual science. They will involve with what? Rate of change. Okay, of course, but then we have different variable. Okay, but whatever it is, they are representing the same equations, which is second order linear with constant coefficient non-homogeneous. Okay, I think that's all for today. Okay, hope you guys will have a very, what you call it, fruitful, okay, and enjoyable semester break. Okay, but don't forget about your study. Okay, stay safe, stay healthy. Okay, I hope you to